Good afternoon, all, and welcome to WMG Group Colloquium. Today, it's my pleasure to introduce Professor Lindsay Greer, who actually doesn't need much of introduction, as most of the metallurgy and material science community already know about his work and research. But it is my responsibility as a host to introduce him to those who doesn't know about him. Okay. So Professor Lindsay Greer, who is currently an emeritus professor of material science, director of research relations, physical sciences and technology at University of Cambridge, UK. Professor Greer's research interests are metallic glasses, crystal nucleation, and grain refinement in casting. He has published some 500 scientific papers and is also the author, along with Ken Kelton, of Nucleation in Condensed Matter, Applications in Materials and Biology, published in 2010. He is the recipient of several awards, including the Griffith Medal in 2009 from the Institute of Materials London and the TMS Bruce Chalmers Award in 2012. At Cambridge, Professor Greer served as head of the Department of Material Science and Metallurgy from 2006 to 2013 and head of the School of the Physical Sciences from 2016 to 2019. Today, he is going to deliver a talk on grain refinement in solidification. Professor Greer, thank you so much for taking your time, and the floor is yours.
So, great pleasure to be with the Warwick Manufacturing Group, but also with many others as well. So familiar faces in the audience, and it means that I'm having the difficult task of giving a talk on a subject that some of the audience are very, very expert about, and others are not. So I'm going to be starting in rather at the basic end, and the experts will have to forgive me for that. So my entry to the world of grain refinement in metals was in fact engaging with industry, notably with Alcan. You can see this large billet here, direct cast billet of commercial purity aluminium. You would get a columnar grain size, grain structure inside this large object, and here's a man for scale. Well, this sort of grain structure with the grains growing in from the faces of the billet would be completely disastrous for the properties. So you have to eliminate it and get an equiaxed grain structure, much finer grains, and this is done, of course, not by testing full-scale billets, but small so-called TP1 samples, which are designed to mimic the cooling rate in the actual process. And this refinement is done by adding chemical refining agents known as inoculants, and that's what the talk will largely be about. I need to emphasize that this business of grain refinement is absolutely essential. I've illustrated it there for the aluminium industry. It's probably its most prominent use, but far from the only one. For those large DC cast billets, you simply couldn't cast them at a reasonable speed if you did not grain refine. The billets would just crack down the middle. You also get advantages of improved surface finish, generally better mechanical properties. And for much smaller castings, the shape castings, you get many, many benefits in the processing and in the properties of the product. So we'll treat this as an essential process, but one which interestingly is very cost sensitive. So we have here, I'm hoping, an ability to see a movie. Will it come on? Let's see. Seems to be reluctant to play, so I shall press on. But what that movie would have shown you was ancient Jackson and Hunt stuff, illustrating the point that, of course, metals are not transparent. So historically, it has been thought difficult to probe what was going on during solidification. That is no longer the case. There have been really dramatic advances in recent decades. You can look through thin samples with X-ray radiography. You can image the grains as they nucleate and grow. Here's some example from Trondheim. Also, dramatic advances in how you can model the grain growth. So the left-hand picture has phase field simulations of these dendritic structures, and the right-hand side is X-ray tomography in action. So no trouble, in a way, seeing these internal structures in castings and models. Modern modeling, and this particular example is 2D, not 3D, but you can model the growth of these dendritic structures and how they float around and move in the dynamic liquid. So I could say that when we ask ourselves, how much of this do we understand? We'd have to say that regarding crystal growth, we understand it rather well. We can model thermal and solutral diffusion, complex shapes, fragmentation, and of course, fragmentation of dendrites is one way that you could stimulate the appearance of new grains. We can look at liquid flow, which stimulates that fragmentation and relates to many aspects of the casting. The great lack in our understanding, at least historically, was the nucleation stage. What are the nucleation templates? What's their population? How various are they in their properties? Where do we even start to model that? And I would want to suggest, perhaps slightly cheekily, that the academic world of solidification studies didn't address this question, because the people interested in nucleation in liquid metals, that's to say the nucleation of the crystals, were primarily interested in how was it possible that that was actually so difficult. So if you have a very clean system, for example, here we have liquid zirconium, levitated, so it's a containerless process, you can supercool that by some hundreds of degrees below the equilibrium melting point, and it remains stable in the liquid state. So people were very interested in that, and it is an interesting topic. But one needs to compare it with what's happening in those DC cast aluminium billets. We could look at the supercooling in those if you have no chemical inoculant added, and you get maybe 5 degrees or so supercooling below the expected liquidus temperature. If you add your chemical refiners, you get fractions of a degree supercooling. So my point is that the supercooling that is relevant in the industrial process, perhaps of the order of 0.2 Kelvin, is an entirely different world from the 200 Kelvin or more supercooling relevant in many academic studies. So in those fundamental studies, we are in the world of a very small critical nucleus radius, a potential breakdown of the classical nucleation theory, and in general, rather uncertain modeling. In the case more relevant for industry, we have potent heterogeneities that are generating the nucleus. It's not a clean system. However, it does mean that the critical radius at such low supercooling is large, and therefore classical nucleation theory should apply rather accurately. But we have, of course, the problem of unknown input parameters. Either way, left-hand column or right-hand column, the quantitative modeling is difficult. Now, nucleation in the textbooks is normally seen as a stochastic process. It involves fluctuations in the liquid that gives you critical sized crystals that in a way hop over an energy barrier. So it's random nucleation events, and it's normally studied under fixed conditions of supercooling. So you can think of a steady state nucleation rate. And for homogeneous, that's to say nucleation in a clean system with no catalytic action, for homogeneous nucleation, our picture is something like this, that the nucleus ideally would be modeled as a sphere. We can then characterize it simply in terms of its radius. As the radius increases, its volume goes up, which gives us a favorable energy term relative to the liquid, but its surface area goes up, which gives us an unfavorable energy term. Summing those two, our overall energy goes through a maximum, and that corresponds to a critical radius. And for radius above that value, the crystal would choose to grow rather than shrink. So that's the standard model of homogeneous nucleation. If we want to stimulate that, we could put into our system a grey substrate upon which our nucleus now forms. The critical radius, that's to say the quantity describing the curvature of the crystal liquid interface, that the surface of this blue nucleus, that critical value stays just the same despite the influence of the substrate, But what obviously changes, depending on the so-called contact angle theta, is the volume of that nucleus. And it turns out that the energy barrier to form the nucleus scales simply with its volume. So with lower and lower contact angle, you get better and better stimulation of this nucleation. But there are lots of problems. When we come to make a quantitative prediction, we simply do not have the numbers at our disposal to put into the equations to get the answers we want. For example, we have no idea what the contact angle is. And furthermore, it would be difficult to measure. And furthermore, it may not even provide a good model for the case we're really interested in, which is low values of the angle with this spherical cap shape may not even apply anymore. And of course, all these substrate particles that we've added to our melt in our inoculant, well, they may not all be the same as each other. So we'd have to model some variety of power or potency of those particles. So it seems like a hopeless position from which to try to start. Well, going way back in time, we were interested in metallic glasses, and they can be made based on aluminium. And it was possible to embed in these some of the same titanium diboride particles that would feature in actual industrial inoculants. These are hexagonal platelets, so the top and bottom faces on this particle are the 0001 faces of the hexagonal system. And what you can see on it is lots of little aluminium crystal nuclei forming on those faces and also on any ledge that happens to have the right orientation. So this would convince us that the crystallography is very important in nucleating the phase, in this case, simply face-centered cubic aluminium, nucleating the phase that we want. There is, however, more to it than that. It was known in the literature that these titanium diboride particles are not really very effective unless you have some excess of solute titanium in the liquid. And in this case, the liquid, of course, is being mimicked in slow motion by the glass. Looking up close at the interface between the boride and the glass, there was something else going on. And this appeared to be reminiscent anyway of something which had been suggested in the literature, which was that in the presence of excess titanium, one would have a thin coating of Al3Ti on the inoculant particles. That's something that has a particularly good lattice match with the face-centered cubic aluminium you would want to nucleate. An intriguing feature of this suggestion was that if you did have, in the real industrial situation, this thin layer of Al3Ti, it would be destroyed when the actual crystal grain grew on top by a peritectic reaction. So the critical layer that might indeed be important for your nucleation would be destroyed by the nucleation itself. So it would be a sort of perfect crime. You would have removed all evidence of the key actor in the process. But the metallic glass process allowed us to capture the time snapshot of that. There were lots of further studies. I should say studies of this kind have been taken much further by the BCAST group, looking in detail at the structures that might form. One could also look at something that was a well-known phenomenon, namely that the action of these added particles, the inoculants, to give us good grain refinement, could be greatly degraded in the presence of some solutes in aluminium alloys, including solutes that are rather important, like silicon. And there have been a variety of studies showing that these solutes could in various ways affect the chemistry on the surface of the inoculant particles and could help us understand why there was a poisoning action. And of course, the motivation would be to help us understand how to avoid that poisoning action and still get effective grain refinement. Well, many of the details of these early studies may have been revised by later work, but the key concept is the same, that we have some way of addressing the chemistry. So where we are then at this point in the story is that we are pretty sure that if you want an effective inoculant particle, you should have lattice matching in some way or another, and surface chemistry will be important. But none of this, however useful it might be, assists us at all in the prediction of grain size. We simply have no starting point on that at all. And we furthermore have the suggestion from those Al3Ti layers that these inoculant particles could in some sense be perfect nucleates. And yet, the refining process is still very inefficient, with less than 1% of the particles actually nucleating grains. So let's look at this idea of a perfect nucleus, and it involves looking again at this business of the contact angle. And that arises from a balance of interfacial energies. And this is a commonly found equation, and the derivation of the angle is straightforward. What the texts often ignored is that you often don't have a solution to the equation. There will only be a solution if the interfacial energies satisfy this rule. And otherwise, you might have a situation where the sum of two energies between the nucleant substrate and the crystal that forms on it, and the interface between the crystal, I used to say, face into cubic aluminium in our case of interest, and the liquid, if the sum of those two interfacial energies is still less than the surface energy in the liquid of the nucleant particle itself. If that's true, then you should actually have a wetting phenomenon where even if the Al3Ti layer was not stable in bulk thermodynamic terms, it would be stabilized by the interfacial energies. So it would exist. And that can be taken further to say that in the industrial setting, you could have a thin layer on your nucleant particle, thin layer of face-centered cubic crystalline aluminium above the melting point of the aluminium, stabilized by the interfacial energies. Well, that was something that had been talked about in the literature, but was probably mostly regarded as a preposterous idea, because if you did have such a stabilized layer, and it would correspond to a 0 theta contact angle, there simply would be no nucleation barrier. The nucleation barrier disappears as your contact angle comes down to 0. And yet we know there must be a nucleation barrier, because you get rather sporadic nucleation of crystals and not nucleation on every inoculant particle. So the idea that there was a barrier known to be seemed to conflict with this idea of a 0 contact angle. But that model for heterogeneous nucleation relies on having the events of heterogeneous nucleation occur as rather small nuclei on what is relative to them an infinite substrate. So the equation that describes the heterogeneous nucleation rate has no number in it at all referring to the size of the substrate. The size of the substrate is irrelevant in that classical picture. But what if that classical picture didn't apply? What if your substrate was actually tiny? What if the substrate was similar in its radius to the actual critical radius of the aluminium nucleus? Well, then the nucleus that would form on the particle would grow outwards from the favored 0001 face, but it would become more and more curved in its interface with the liquid, and that would make it, at least to begin with, much more difficult to continue growing, and you'd have a critical barrier that it would have to break through, which is past the interface of maximum curvature, that's to say smallest radius of curvature, and that after that point it could then grow more freely. This picture, as shown here, may look rather similar to a bubble, and it would be a perfect sphere in the case of a gas bubble in a liquid. In the case of our aluminium, it's growing not on a circular disk of TiB2, but something that's much more like a hexagonal platelet. But the shape of the interface between the crystal and the liquid is still pretty close to a hemisphere at the critical point, and so we can model it as a hemisphere without too much worry. But here's the resemblance with bubbles, and of course, if you want to blow a bubble out the end of a pipe, there's a maximum pressure at the point where the bubble is shaped like a hemisphere, and that corresponds to the critical nucleus state for the bubble, and is a exactly corresponding state for the crystal state in our aluminium nucleation on a small substrate. And here is the evidence that for a typical critical radius that we expect, and we know what that is because we know, after all, the supercooling associated with it, we can compare that with the actual size of inoculant particles, which are perfectly measurable, and they are comparable. That's the point. So our standard heterogeneous nucleation theory of infinite substrate and small nuclei simply doesn't apply. The nuclei and the substrate are similar in size automatically. That means we're in a realm of what, in really ancient work, David Turnbull would have called athermal nucleation. So you can imagine a high temperature system, it has a number of embryos within it, and you cool the system. As you cool the system, those subcritical nuclei, the embryos, become critical as the critical size changes, in fact decreases, on cooling. So the way Turnbull would have described it, these embryos, which are subcritical, they're not going to grow, will grow. He described it as they are automatically promoted to become nuclei when the critical size decreases and sweeps below their own size. So they're switched on at a critical supercooling. This is the value of that critical supercooling. And the key point for us, setting aside the thermodynamic parameters, which are known and measurable, is that critical supercooling is inversely proportional to the substrate radius. So the grain will start first on the largest substrates. I have tended to call this grain initiation and not actually nucleation, because I think it's not strictly speaking nucleation. The crystal already exists on the substrate. It's not a matter of is it nucleated or not, it's a matter of does it grow or not. This is how the energy would look. You will remember that for homogeneous nucleation, you simply have a maximum in the formation energy of the nucleus, and that defines a critical radius. In this case, you could imagine having a substrate particle with a crystal already existing on it as a thin layer. This would sit in a minimum of energy here at some temperature, and were it to grow, the energy would go up. That doesn't happen. But as we lower the energy of our system, the entire nucleation system evolves following this set of curves. So the barrier to get a fluctuation of a heterogeneous nucleation event becomes lower and lower, but eventually the barrier disappears altogether. There is no maximum. And that is where you suddenly get the nucleation occurring stochastically. It's not deterministically, it's not stochastic. There is no barrier to jump. So it's switched on automatically as you lower the temperature. If you were able to measure the size distribution of particles, is something that would enable you to pull out a distribution of supercoolings at which the inoculants would become active, and you could feed that into your model. And this sort of picture had been fed into models for a long time, but without a fundamental justification of the shape. But understanding the stochastic going to deterministic model for nucleation enables us to predict exactly what that shape should be of just how many nucleation events you'd get as you increase the supercooling. This all looks highly promising, but there's something still missing. So looking at what we had already, that is matching. Yes, we need that for a good inoculant action. We need the right surface chemistry. We may have perfect nucleants, and yet only about 1% or less of the particles seem to do anything. Well, you could take a different world. This is crystallizing calcite from a water-based solution, and it's forming little heterogeneously nucleated crystals on a substrate, and they appear sporadically. But what one can identify in the middle is a larger crystal, which must obviously have nucleated earlier, and it has sort of bleached out the region around it. We could ask, well, why are there no nucleation events close to this early nucleation event? And the answer is, in this case, rather simple. It's just that there's nothing wrong with the substrate. It's just that the solute level has been lowered close to this nucleation event by the fact that something was already growing there. So there just wasn't a sufficient supersaturation of solute to give us effective nucleation. So you have this gap. Well, would that apply in our alloy solidification case? Well, you can look at the gap between the particles that actually give you nucleation events. In a typical system, it might be 10 microns. And you could ask, for the solidification conditions we have, looking at the solute levels in the aluminium, how far would this solute diffusion field extend? And the answer is about 1 micron at most. So what this is saying is, yes, of course, you get solute depletion or aggregation enhanced level around an aluminium grain that's already nucleated, but the extent of that influence is not sufficient to reach neighboring nucleation events and thereby influence them. So something else must be going on, and it's not diffusion of solute. It is, however, diffusion of heat, because obviously thermal diffusivities are so much higher than solute diffusivities. So what this is saying is that an early nucleation event releases latent heat of solidification, and the other nucleant particles in the system soon get to know about that through the change in temperature. So this is an early model of Maxwell and Hallowell that said as you cool the system, you get more and more grains nucleating, they grow, they release more and more latent heat, and eventually the release rate of the latent heat dominates over your external heat extraction. Your temperature then turns around, you get recoalescence, reheating, and of course that switches off having any more nucleation events. So our picture then is that you have a distribution of particles of different size. We've already, these are the inoculant particles on which we'll nucleate our face-centered cubic aluminium grains, and it will occur first on the largest particles. And the critical nucleation diameter
radius is temperature dependent. At high temperatures, it's high, but as we lower the temperature, that radius goes down. Nucleation switches on at smaller and smaller particles, but eventually you get enough growth from enough particles that you release latent heat fast enough for the temperature profile to turn around, and you get reheating, recoalescence, rather than continued cooling. And that means that these smaller particles never got their chance to nucleate the aluminium. They, unfortunately, numerically, are the majority. So it immediately accounts for why most of the particles, which if you look at them microscopically, look perfectly fine. There's nothing wrong with them. They have the lattice matching, they have the right chemistry, they just never get their chance because they're too small. And that is what we call the free growth model. And it's essentially a thermal model. And the key point is that you have all the parameters to put into the model. You have the thermodynamic parameters, and you can measure the size distribution of the inoculant particles. And when you put that in, you can ask, well, as a function of how much refiner we add, what grain diameter would we expect? And with no adjustable parameters, you get a pretty good fit. Data on the effective cooling rate are slender, but insofar as there are data, again, it's quite a good fit. The point is, if you extract heat faster, you overall can compete better against the latent heat release and recoalescence, so you can get down to a lower temperature before the onset of recoalescence, thereby switch on more nucleant particles and thereby get a finer grain size. So the effective cooling rate can be understood. Solute is a thing you need in there in order to slow down the growth of already nucleated crystals. This relates, of course, to the partitioning of solute in the phase diagram, and I won't go into the detail, but it turns out that the effectiveness of that partitioning in slowing down the solidification rate is this parameter Q, the so-called growth restriction factor, which relates to the slope of the liquidus in the phase diagram, the partition coefficient, and the content of the solute that you have. And you will have different Q values for different solutes, and to a first approximation anyway, you can simply add the Q values for different solutes to get the overall effect. And you can look at how the grain size comes down as a function of the overall growth restriction factor. And again, a good fit overall.
Looking at that growth restriction factor immediately enables one to understand the common chemistry of inoculant systems, that the ones used in aluminium, we've already hinted at, were titanium boride particles mainly, but with excess titanium, and we can now see the real relevance of this excess titanium. It may be to do with the surface chemistry on the particles, but it's certainly also to do with the growth kinetics. So for a given amount of solute added, the growth restriction is by far higher for solute titanium than it is for any other solute in aluminium, which means that any aluminium grain that's nucleated in the presence of solute titanium grows particularly slowly, thereby impeding the recoalescence, enabling you to get lower temperature and to get better grain refinement on smaller and smaller particles. The converse in magnesium is not titanium, but zirconium, again well known as a solute associated with effective grain refinement. This is work again from Trondheim, just showing that, again, if you have all the parameters to put in and they're all independently measurable, you can get good predictions of grain size and number of grains per unit volume and so on. So the model basically works. So when we come to predict grain size, then very few of the particles added work. It's largely because of latent heat release, and your input is a measured particle size distribution, and you can make quantitative predictions. It does enable us to probe, purely in a modeling sense, how good is a commercial refiner compared to its optimum level, especially if you're only sampling this dark region here of particles that actually do anything. The smaller ones, which of course are plentiful in population, simply don't do anything. Well, you could just model the idea of keeping a similar particle size distribution, but changing the mean particle diameter for a given spread of the distribution. And if you made the particles too small, of course, they're not very effective because they're small. So your grain size would go up. It's this dark black line. So you don't want to be too small. You don't want to be too large either, because for a given amount of added refiner, I'm now thinking here of weight percent in our system. For a given amount added, of course, your grain, you'd have fewer and fewer particles if they're larger. So again, your grain size would go up. You just have fewer nucleating particles. Somewhere in the middle, there must be an optimum. We can calculate where that is. And the red box happens to be the size arrived at in industrial refiners purely by trial and error, without understanding any of these underlying processes. So I don't know whether we should come away profoundly encouraged or profoundly discouraged that a quantitative analysis has shown that trial and error could get there first, or at least pretty close. It's generally considered that existing industrial refiners are pretty well optimized. It's not totally true. You could imagine getting a better number efficiency of the refiner, and you would do that by changing the size distribution of the refiner particles to be narrower. And by changing the distribution, you can indeed get an overall smaller grain size. There is something to say, though, about how disastrous is this? If I were to ask, looking at the number of inoculant particles in our system, what's the fraction of them that actually do anything? The answer is about 1%. But remember, the ones that do something are the big ones. So I could ask not what's the effective number fraction, but rather what's the effective volume fraction? And that is very high, 80, 90%. So in fact, the system is not as bad as we might have thought in terms of the volume of the titanium diboride particles doing some work. It's better than we might have thought. Now, something I haven't mentioned explicitly so far is that, in effect, what we have been looking at in a grain refining action is forcing a transition from columnar growth of grains to equiaxed growth. So our system, we are imagining, is cold on the left, hot on the right. This is a picture due to John Hunt. And our solidification is proceeding from the left to the right,
you would naturally get columnar growth. But if you get enough nucleation, and that's where our inoculant particles come in, if you get enough nucleation ahead of this front, then the equiaxed grains will block the columnar front, and you'll switch to equiaxed growth, which is what we want. And you could look at the key parameters for that transition to occur. It would be the temperature gradient. Obviously, a high temperature gradient would make things even hotter to the right, so it would be even more difficult to get nucleation. That would favor continued columnar growth, not the equiaxed that we want. And the other key parameter is the overall rate at which this interface advances. So we can make a map which maps out regions where you expect the desirable equiaxed growth and the undesirable columnar growth. This picture is useful to have in mind when we consider the modern interest in additive manufacturing. This is just a figure lifted from a paper to illustrate that, of course, things are highly complex. But in all of this, we should just look at how some of the key parameters vary from the more conventional solidification. Our melt volumes under our laser tip might be much smaller. We might have rather similar crystal growth velocities. Cooling rate we might expect to be higher, for example, in laser powder bed fusion. But the really key one, the deadly one, is the temperature gradient, which is very high. And that, remember, is the thing that will kill off our chance of equiaxed growth. To give you a sense of how bad the situation is, here's the plot I showed you before, and the data here and the lines, the mapping out on the diagram are for a conventional, for example, DC casting of aluminium picture. If you took the typical temperature gradient in our laser powder bed fusion, it moves you way over to here. So deeply, deeply in the columnar region, but you do have a higher, potentially higher solidification rate, possibly off scale on the top of the slide. So it's putting us in, at the very least, we'd have to say, a regime that's very different from that which is mapped out in conventional treatments. And so more work is needed. But for sure, we will have to work hard to continue to get a fine grain structure throughout one of these systems, because they're just made through remelting, if nothing else, to recultivate columnar grains all the time. Final bit of talk, I want to switch to something apparently different, but with links to our alloy solidification. And it's what can we learn from nature, and in particular from the northern wood frog, which has attracted a lot of attention, lives in North America. By the time you go far enough into Canada, far enough north, it goes coast to coast. It's cold-blooded, of course, but it lives north of the Arctic Circle. Bad life choice. So it means in winter, it will actually freeze. It goes completely solid. It's roughly 40% ice, and the rest is a sugar glass, and all the systems shut down. And yet, come the spring, it thaws out and hops off. And ice formation in cells is normally utterly fatal to a system. So the fact that it's not fatal to the frog has attracted a very great deal of research attention. And the secret is that, in fact, it does avoid ice formation within its cells. Let's first of all look at what goes wrong if you get ice formation inside a cell. So the cell's a little bag of a sugar and salt solution with a membrane around it. Ice is essentially pure H2O. So if you form ice in the cell, the liquid in the cell becomes more concentrated in solutes. That upsets the osmotic balance between the inside and the outside, which simply draws in more water, which allows the ice to grow even more. So the cell will continue to expand by pulling in the water, and it will eventually burst. That is the thing that kills the cell, not the actual volume change going from water to ice itself, which is of itself not enough to rupture the membrane. So cells will burst, your organism is dead. What the frog does is cunningly put what we might, as metallurgists, call inoculant particles outside in the intracellular fluid to ensure it knows that ice will undoubtedly form. What it makes sure is that ice forms in a safe place.
namely outside the cell. So all of our processes now go in reverse. The solution outside becomes more concentrated in solute. The osmotic balance now draws water out of the cell, which dehydrates. Nature is quite happy with dehydration if it has enough sugars in the system, and it forms a glass. So the system sets solid, but happily rehydrates in the spring. So what we can say is that this is a wide, I've illustrated it for the case of the frog, but this idea of frost giving you ice and damaging cells or not is important for bacteria and important to avoid for animals. They're not very good at it. So the frog, and remember, for the frog, nucleating that ice outside the cells is a matter of life and death. And the critical supercooling is in this sort of range, 3 to 12 Kelvin, not the 0.2 Kelvin that aluminium metallurgists can manage. Why is it so bad? Well, it's because it cannot make very big substrates. So those inoculant particles in the aluminium were some microns, proteins, and they are very effective at mimicking the hexagonal structure of ice, but they're not effective at growing to large surface areas. They prefer to fold into small areas. So the maximum we can manage is about 30 nanometers, and that corresponds, of course, to a higher supercooling, since, as we know, the nucleation occurs with greater difficulty on smaller particles. You can map what the supercooling is as a function of the radius of these ice nucleating agent disks, and it fits our free growth model perfectly. You should be aware that these biological ice nucleating agents are commercial. They're used in making artificial snow. You should be aware that bacterial ice nucleating agents are very effective in nucleating ice crystals in the atmosphere, which turn out to be important not only in snowfall, but in fact in almost all rainfall. So there's now a great deal of interest in generating these and projecting into the atmosphere to increase cloud cover and therefore increase the reflectance of sunlight back to the sun and help with global cooling, should we need to do that in some sort of climate emergency. But I should also mention another approach that nature takes to avoiding the problems of cold temperatures. And that's an entirely different approach adopted by Antarctic fish. Lots of species, shown here, live their entire lives, birth to death, with their blood below its own freezing point. Heaven knows why they do that, but they do. And the freezing is inhibited by the presence of antifreeze proteins, these AFPs, which exist in various types. You would think these would act like antifreeze, in other words, changing the freezing point of the blood, changing the thermodynamics, but they do not. Their action is instead kinetic, not thermodynamic. And what happens is in the presence of ice, the ice should grow thermodynamically, but is prevented from doing so because these proteins attach onto the growth ledges. It effectively stimulates, so you could take this supercooled blood, actually seed it with ice crystals, which thermodynamically should grow, and they don't. But it's only effective for rather small supercoolings. But of course, exactly small supercoolings are relevant for our metallurgical processes. It has led to some interest in the literature, given that those antifreeze proteins must accurately mimic the structure of the ice in order to latch onto the ledges. And of course, the nucleating agents also had to mimic the structure of the ice to act as good substrates. They must in fact be rather similar to each other. And the question is, if you put them both in a solution, which will win? And here they are supposedly fighting it out. Well, the truth is, if you study the supercoolings you can reach, not just with the ice nucleating agents, the big things which are effective at nucleating, but also the small things, these antifreeze proteins, which are famous for counteracting freezing, can themselves act as perfectly good nucleation substrates because they have the template of the ice structure. They just would nucleate at a very large supercooling. But it's all one behavior. And furthermore, when you quantitatively fit it, it matches the expected solid liquid interfacial energy of the system. So everything fits. It does lead to the idea that those two particles, the antifreeze proteins and the ice nucleating agents, though opposite in function, might have a common evolutionary origin. We could then ask, well, would there be an equivalent, since we know there's an equivalent in the inoculation end for metals, is there an equivalent at the antifreeze end? Could you inhibit growth without needing solute in the melt? And there are examples of this where you modify growth patterns, for example, of graphite in cast irons. Difficult to imagine doing that for metallic phases because the growth is not obviously mediated by ledges onto which your antifreeze units could attach. Nonetheless, there are examples of growth restriction not by solutes, but by nanoparticles, which as far as we know don't template onto the thing that grows, but block its growth. And insofar as you have an action by nanoparticles, it's mostly attributed to nucleation, that they might act as nucleating substrates, but might they instead be acting due to growth restriction? Well, there is work on that. This is an example of a liquid-liquid phase separation where you don't want a coarsening of the liquid aluminium bismuth two-phase solution, but you can inhibit the coarsening by having a population inside of nanoparticles that coats the liquid droplets. And there are emerging studies of growth restriction giving you a reduction in grain size, but with that growth restriction could be due to nanoparticles as well as solute. Trouble with nanoparticles is you need rather a lot of them, and they probably cost you quite a bit of money. So at this point, the nanoparticle way of getting growth restriction is probably not very cost effective compared to more conventional solute action. So the final slide says grain refinement of alloys, I think, is essential in solidification processing, both for small scale cast and wrought alloys. Essential for the processing, but it's also essential for the products of the properties of the products. And there are new challenges as you develop new processing methods. It relies on things happening at small supercooling and on restriction of growth. Quantitative predictions are possible, unlike what might have been thought to begin with, and that's because you can base your analysis on the size distribution of the particles, and that, of course, is something that's perfectly measurable. Are there lessons from nature? Well, there certainly are parallels with nature, and I would suggest that the next thing to look at more closely is growth restriction. So I will end there, Prakash, and perhaps stop sharing. Would that be a good idea?
I wanted to make a quick comment about trial and error. As I get older, I get more and more keen on trial and error as the best method of finding things out. You made a very interesting comment about how perhaps trial and error had found the right answer, and you know, it's very encouraging, perhaps in one way, to think that when you get the right theory, which I think you're hoping that you've got, or you believe you have, that it explains things. But that tends to be a bad way of going to start with the theory. It's better to do the trial and error first. Well, of course, the comment I wanted to make is, as I've increasingly looked back into history, when I wrote my book on the equations of materials and did biographies of some of our well-known fundamentals, and in particular, I did my history of the development of humankind as the first chapter of my book on high entropy materials. I increasingly have realized that I had a complete misconception about the scientific revolution and what science was. Or at least I didn't have a complete misrepresentation. I had a rather subtle misrepresentation. It's all about trial and error. So, you know, theory in a sense is no better than the original Platonic or Aristotelian or arguably Christian or Confucian great ideas, which have, you know, in many cases proved to be wrong. The whole point of science is to go out and look, see, and find out. And we should always bear that in mind. And, you know, even the greatest, all our wonderful quantum mechanical theories and Newtonian mechanics and Maxwellian electromagnetics and Darwinian evolution, whatever, are other great theories which have some basis because they link to experiment, but it's the experiment which is what it's all about. So I like trial and error, and I just wanted to make that point because you made it very, very nicely.
Very interesting and a good point.
Hi, Professor Greer. Thanks for your talk. It's very interesting. I have two questions. So your model, you can predict the nucleation, critical nucleation size of the inclusions you put in, you only saying that only big ones will encourage the nucleation, and but there are many small ones, and you also mentioned that the smaller ones can refine the grain size. Are they enough to have an effect on the growth of the grain size?
Well, that's your first question, which I'll deal with, and then you'll get to your second one. So the answer, unfortunately, is no. So the population of those small ones is not high enough to have a growth restriction effect. You would have seen maybe very quickly in one of my little pictures with the bismuth droplets inside liquid aluminium, that essentially the droplets whose growth you want to stop become completely coated in the nanoparticles in the case where the growth restriction is effective. When you work out the volume fraction added of the nanoparticle phase, it's very high compared to the parts per thousand that would be typical of a normal grain refining process. So your instinct is correct that the nanoparticles could, in principle, inhibit growth, but there just aren't, the small ones, but there aren't enough of them.
So this is based on your prediction of your model, or this has been validated by experiments?
I think I would say that my model doesn't give any firm prediction on that particle action on growth restriction. We've had some thoughts about it and done some very primitive modeling, but there is now quite a lot of experiment on it, which shows that nanoparticles can indeed give you growth restriction, but you need really quite high addition levels, and that is quite well understood, or at least well characterized experimentally.
Okay, thank you very much. Another small question. So in your model, I remember you indeed consider the chemistry of the inclusions on the effect of the nucleation. Do you consider the chemistry?
Just a quick comment is chemistry is undoubtedly important, but of course the only bit of the inclusion that the melt sees is its surface. So it's really the surface chemistry that's critical.
Yes. So you in which term your model considered the chemistry, surface chemistry?
We were not explicitly considering that, other than to say that you needed the right chemistry to, in effect, have wetting of the particles by the crystal that you were trying to nucleate. And I think later work than ours has done a much better job of understanding how you actually tailor that surface chemistry to achieve that.
Okay,
but what I would say is that, again, it perhaps relates a little bit to Brian's trial and error point. Both nature and mankind, by trial and error, I think, has come up with nucleating particles that are already wetted by the phase they want to nucleate. So in terms of the surface chemistry, they are as perfect as they could be. The remaining challenge to actually forming the grain is providing a big enough surface for it to happen.
Okay, very clear. Thank you very much. Thank you.
Brian, your hand raised. Any further comments?
Yeah, can I ask another question?
Yeah, please.
So a slightly more technical question about the grain size. So if I understand how it all works, the implication is that if we want to do proper metallurgical engineering, so to speak, or control our microstructures, whatever phraseology you want to use, but if we want to get a small grain size most efficiently and effectively, the right thing to do, and you didn't kind of complete the point, it seemed to me. So am I missing something, or is it just that this is difficult to do for some reason? It seems to me to point to the notion that what we want to do is the big particles are the ones that cause the nucleation. The small ones are there kind of by happenstance because we've got a particle distribution and they never get to a figure in it, and probably cause problems because they act as sort of little particles which can cause mechanical failure and problems later as acting as just impurity particles in the system. So what we really want to do, and we got loads and loads of them, potentially causing premature early fracture, although that also is somewhat size dependent, and the smaller they are, the better. But nevertheless, fractures in materials start from those sort of places. So what we really want to do is we want to find a way of breaking our grain refining material up with its correct chemistry into the right size particles without all these little ones knocking around. I mean, it seems to me that what we've got is an extremely inefficient method of getting the right big particles at the right size to give perhaps the right smallest grain size we can get, but we brought with it a whole bag full of pretty useless small particles that are just potentially causing problems.
I think there's a lot in what you say, Brian, and that was part of the thinking lying behind the idea that you could optimize a refiner by changing the size distribution.
Yes, you said that.
There would be the idea, perhaps, that if you were able to get a very narrow size distribution, where would you put it, actually? You might want to have a lack of the largest particles, so you can actually get to deeper supercooling before it all happens, and then a lot happens. And Fan, of course, has worked a lot on this idea of explosive nucleation. That seems to be opens up an interesting challenge, because you could design a system that, when it works as you intend, gives you a wonderful fine grain size, but is at risk of accidental triggering of early nucleation events by something you haven't controlled. The few large particles you didn't quite manage to get rid of. So that's the other thing to think about in thinking about ideal particle size distribution, is how vulnerable are you to other influences in the system that were not fully under your control.
Hi, Prakash. Hi, Professor Greer. Thanks very much for the talk. I'm Rodolfo from the School of Engineering. I just had out of curiosity here, a question. Wouldn't having this distribution of particles, some of which are nucleating, some which are not, wouldn't it by any chance cause any segregation upon the cooling?
What do you mean by segregation? Because you could be meaning the solute segregation in the liquid,
yes,
or you could be meaning segregation of the particles themselves, which of course could be subject to some settlement.
Yes, more on the first case. As we cool, as with the production of the casting itself, wouldn't segregation be of a concern?
Well, it of course is a really important phenomenon throughout all of this solidification. I was mostly working on commercial purity aluminium, so not high solute levels. But the solute levels are absolutely critical in understanding the growth phenomena. And there's been quite a lot of work on how you would have local effects on the nucleation because of local changes in the solute level. I consider that an area where the modeling is tricky, because it's not difficult to find diffusion-based models of solute fields. But of course, the liquids in real systems are much more active than static liquids. And so the local flow velocities will have a critical influence on the behavior.
Really, it was a nice presentation. But yeah, some people were discussing about, the nanoparticle on aluminum powder. I mean, we did, I'm from GKN Aerospace, Alphonse Anthony Sami from GKN Aerospace. So I work a lot on aluminum additive manufacturing technology. So basically, we had some interesting meeting with the Caltech University. I think I can't remember the name of the company. It was a spin-out from the Caltech. What they did in additive manufacturing, as we said, the cooling rate was very high. They introduced titanium carbide nanoparticle onto the powder and then mixed it, and they did showed us, very good property. But only thing is, you also pointed out before that, it was so expensive. It doesn't make any business case from a company point of view. We just had a nice meeting, but we couldn't make it. I think somebody was questioning, but yeah, there are practically some papers, and definitely, when you were going through your slides, I was just literally in my mind, it was going through some of the work we were trying to explore with that particular company.
Yeah, it struck me in general with the work on added nanoparticles that you did have to add a lot compared to the addition levels of a conventional refiner, and that was just not going to be very difficult for that to be cost effective.
Yes, they did show, I think I remember 15%, 30%, kind of that range of, then it becomes, metal matrix composites rather
yes, it
than
becomes a composite material.
Yeah,
indeed,
exactly.
Yes.
So I just was like not really pleased. But the grain size and the strength and things, percentage, without sacrificing the percentage elongation, the strength was also very high. But just to make a comment. Yeah, thank you. Such a nice presentation.
Thank you.
Thank you. Thank you. If no more further questions, it's already 2 o'clock, 2:04. So I once again, on behalf of WMG, thank you, Professor Greer, for taking time and presenting such a wonderful talk to our group people. And I hope all enjoyed. So thank you very much and good afternoon.